So this is just a little bit more about Young's modulus. I know it was in a previous video, but in case you just want to skip straight to Young's modulus. And if I have a material and I'm looking at the stress strain diagram, in this linear part right here, the slope is Young's modulus. And it is, as long as you're within the elastic part, you're good with that. And it's the point where the molecular bonds will stretch, but will still return to the original shape when the force is released. It is, in essence, because I apply a force here and I'm pulling it out, there are forces within the material that are trying to pull it back into normal. That is the force that is causing the stress. And so when you release this external force, it's the stress that brings it back. It does relate to Hooke's law very much. And in the other video, we do more direct connection between Hooke's law and the stress-strain relationship. So the units are pascals. It is not a pressure, but it still has the same units as that. And so if we're looking around, so if I know the stress and strain at any point during this region right here, assuming that it does go through the origin, then I can find the Young's modulus just by dividing the stress over the strain. If I'm looking at some of those other variables that I've used before, 1 over Young's modulus is the longitudinal strain over the longitudinal stress, which is alpha. So y is just 1 over alpha, and that will come in handy later. Now Young's modulus, just as an example for aluminum, is 6.89 times 10 to the 10th pascals. Now typically, well, I shouldn't say typically, some places will not do it in terms of pascals, but they'll do it in terms of gigapascals or megapascals. So this is also 68.9 gigapascals, and this would be 207 gigapascals for the Young's modulus of steel. And in terms of PSI, I have those values over here. Now, one of the questions that I had was, if I pull on it, I get the slope here. Suppose I push and it compresses. And so if looking at the absolute value, do I still have basically the same slope? So does Young's modulus work for compression as well as for tension? And the general consensus is yes, it does. However, the elastic limit is not necessarily the same, because with concrete is designed for compression. It's not really designed for tension. And so concrete, for example, I think it's a classic example there, will fall apart much more quickly if I'm pulling on it than pushing on it. Now, there is one source that actually then qualified it and said that Young's modulus is the same for compression and tension as long as it's a linear isotropic Hookean material. Only one source actually used that qualifier in there. It seems legitimate, but I think the rest of it, couldn't quite tell whether it was just understood or whether they were making more universal comments about the nature of Young's modulus for compression or tension. But for what we're concerned with here, we will assume that they're the same. We'll assume that it's the same for any material unless I state otherwise, but the elastic limit is not necessarily the same.